Okay, so this is John Wood with Clément Pit-Claudel. So now let's say you want to do a project in Dafny, and in particular you want to verify a small compiler in Dafny. So you would typically start by writing a simple version of the source AST, and then write some predicates, and then start doing some proofs. And at the beginning of a project, everything is very simple, and so you can really benefit from Dafny's high level of automation. So everything goes smoothly and very quickly. And then you start iterating, so you complexify your definitions, you make some updates, and you start updating the proofs. And while you iterate, the proofs tend to become more and more complex and unstable and take more time. And also they have some random breakages. Now, a big issue is when the proof becomes unstable, it's very hard to understand why it becomes unstable. And when a proof breaks, you don't have much information. You don't have much debugging information, and in particular, you don't have a context to look at so that you can understand what is going on and fix it. And one big issue with that is that while you progress on your project, you tend to spend more and more efforts into going further until you hit this wall behind which you can't really make any progress. So this is a very painful situation. And one question I'm going to tackle is, can we have a trade-off by which you invest a bit more time in setting up the project and structuring it correctly so that you have better iterations later and you can scale up more? And like in the previous talk, I'm going to focus on inductive proofs. So let's look at a very small concrete example. You want to do proofs about lists. So you have this list data type and the obvious append function. And now you want to prove an associativity lemma about append. Now at this stage, you can really leverage Dafny's high level of automation. And actually by just asking Dafny to use the induction tactic, you get the proof which goes through automatically, and it's true for many other such proofs. But now you want to iterate. So for instance, you add a snark case into your list, for instance. And now the proof fails. So you need to debug it and fix it. So you dive in, and in order to dive in, you explicit the inductive structure of the proof by doing a match on the first list, listing all the cases, and then you look at the cases one by one. So you start with the nil case, it goes through, this is great. Then you look at the cons case, and now it fails. Now, at this point, I actually already start scratching my head to try to understand what's going on by closely looking at the goal. And in more complex examples, I would actually grab a piece of paper and a pencil and start writing things down. So in the present situation, you're in the cons case, so if you substitute L0 with the cons of HT in the goal, you get this, and then there are some things which simplify out until you get there. And here you see you have those two terms which you need to prove are equal, and you can get this by introducing the proper recursive call, and things go through. And now, at this point, you can finally look at the snark case, which is the problematic one. Now, just before going further, I want to call your attention to the fact that if you look at the nil and the cons case, the structure of the proof closely follows and actually duplicates the structure of the append. We'll go back to that later. So now, let's say you anticipated a bit, and you knew you would have to make updates and the proofs would break eventually. So in order to make the iterations easier, from the very beginning, you detail the structure of the proof. And you will likely do it this way, by doing the interesting cases, the cons case here, and leaving the other cases to be automatically proven by Dafny by having this case underscore, right? So now you add the snark case. What happens? Well, Dafny will tell you, I can't prove the underscore case, but you don't know which case it is about. Now, of course, in this situation, I just added the snark variant, so I know it must be about snark. But in other situations, there may just have been a proof instability which certainly broke, and you don't know which variant it is about, okay? So now, let's say you were a bit more conservative and you actually listed all the cases, like nil. Well, actually, what is likely to happen is you will forget to add the snark case in this proof, and if you don't do so, Dafny will consider you omitted it because you consider it is unreachable and you try to prove that it is unreachable. And it can lead to inscrutable error messages, especially, for example, if it times out. So now let's contrast that with what you would do in an interactive theorem prover, say Coq. So it's very easy to port those definitions for list and app, and this is a way of doing the associativity proof. Now, something important is you're actually not expliciting the inductive structure of the proof. You would use the induction tactic to apply an induction principle, right, on the first list. And then it would give you two goals, one for the nil case and one for the cons case. And particularly in the cons case, you would automatically get the proper induction hypothesis, which is actually all you need to finish the proof, right? So this is something pretty good. And also, actually, you would more likely write it this way. You would try to discharge as many subcases as possible and focus on the interesting cases like cons. So this is a bit equivalent to having this case underscore on the left. So now once you add the SNOC case, what would happen is, of course, the proof would break, but it would tell you there is an unsolved goal here for the SNOC case, and you can have a look at and directly dive in and solve it. So we want to kind of take this good thing on the right and port it to the left. And more precisely, there is something which works very well in interactive theorem provers, which is the use of induction principles. So we want to use that and the benefits which come with it and port it to Dafny and combine it with Dafny's high level of automation. So there is actually a way of encoding induction principles in Dafny, and we can do so by using abstract modules. So the trick was as follows. You define this list induction module in which you declare a predicate P, which is the property you want to prove. And then you declare some lemmas for all the cases in the induction, so induct nil, induct cons, etc. And given those lemmas, it is possible to prove once and for all that P stands for the list, right? So you do this lemma once and for all. Now, when you want to use this induction principle, all you have to do is define a module which refines list induction and then fill in the holes. So you would define the predicate P, and of course you would have to do the proofs. And in the present situation, the proofs go through automatically. The reason being that all you need is the inductive structure to be set up, and then Dafny's automation can take care of the rest. And this is actually the reason why, on the previous slide, in the initial version of the proof, the induction tactic would work, right? So now you iterate. So you add the SNOC case. So of course you need to update the induction principle to add an induct SNOC lemma, and you need to update the induct proof. But then for all the proofs which actually use the induction principle, what would happen is if the induct SNOC lemma doesn't go through automatically, Dafny would tell you, I can't prove induct SNOC. And so you immediately jump in, dive into the interesting part of the proof, and start fixing things out without having to really debug what's going on, or at least you have less work to do. Now, this works on a very trivial example, which is this list example, but it actually works on more interesting examples. So, for example, this was inspired by a work-in-progress verified compiler for Dafny, which is around 10,000 lines of code and proofs, and is publicly available. And the issue we had when working on this compiler is that the semantics in Dafny are defined by using with an interpreter function, so this interp statement function, which is around 1,000 lines of code. Now, a problem was whenever we had to make a proof, for example, whenever we wanted to check to verify the correctness of a macro pass, we had to prove something about this interp statement function. And as a result, we had to duplicate the structure of this function. So basically, you need from the very beginning to have 1,000 lines of code for all your proofs, which is a lot of clutter. So this is what motivated the introduction of this induction principle. And of course, we also had all the other proof instabilities. So let's illustrate how it works on a simplified version of the Dafny language. We'll call that Mini-Dafny. So you have this interp statement function, which takes as input a statement and a context, which is just a map from variables to values, and it returns the value the statement evaluates to. So we mix statements and expressions here, and we say for illustration purposes that all values are integers, and it returns a new context. In the case of sequences, we just change the execution of the elements in the sequence. Now, the question is, how can we encode an induction principle for that? And for this, a good way of understanding what is going on is to go back to Coq. If you wanted to encode the semantics of the language in an interactive theorem prover, you'd write it as an inductive relation. And after you've defined this relation, you would get an inductive principle that you apply when you want to do your proofs. So this is what we're going to encode. We're going to encode the inductive principle resulting from the encoding relation we want. So it's slightly more complex than we list, but it's not that difficult. And in particular, we need a few more auxiliary predicates. For example, we need not only the predicate P, which is what we want to prove, but also a P-step predicate, which allows us to mention intermediate steps of execution. And in the case of sequences, this gives the following. Okay, so the lemma for sequence, in the lemma for sequence, we mention the intermediate step, which results from evaluating the first element in the sequence. Now, for this Mini-Dafny language, we apply this induction principle on several proofs. Like, for example, we defined a predicate is pure, and we proved that if a statement satisfies is pure, then evaluating this statement leaves the context unchanged. Something interesting is that the proof of is pure is quite simple. All you need to do is, once again, to set up the inductive structure of the proof. And then, once we've done that, Dafny's high level of automation takes care of everything. So here we just had to instantiate the inductive principle, and then we got the proof for free. We also verified a small pass which eliminates multiplication by zero, so expressions of the shape 0 times some expression, provided that the expression we eliminate is pure. Otherwise, you can't not evaluate it. And the good thing here is, if you don't have an induction principle and you want to do this proof, you have to set up the structure of the proof. So you have a lot of work and a lot of clutter just to set up the proof, and before you can actually focus on the interesting elements. Now, when you use this inductive principle, all the boring parts of the proof go through automatically, which allows you to focus on the interesting part, which is the multiplication case, right? And finally, we also verified a small property about a variant change predicate, which checks whether a statement leaves a variable unchanged or not. It might seem trivial, but we actually need that for to verify an inline pass in the bigger development, and it actually proved a lot harder than what we had expected. And we also checked what happens when we iterate on the AST. I will not detail that, but the important point is whenever we updated the AST to make some modifications in the language, we of course had to update the induction principle, but then whenever something broke in the proofs, we were able to quickly, we had a very specific lemma that we were able to look at so that we knew what was going on. And because those lemmas are small and simple, it's the response time is very quick, which means you can very easily iterate and understand what's going on and fix the proofs. So overall, it led to a far better experience when iterating on these kind of rules. So thanks for your attention. Yep.
Hi, thank you for the very interesting talk and work. So originally at the beginning, you gave it like a sort of initial motivation for introducing induction principles, given that Dafny treats missing cases as unreachable cases, and that renders using a match to sort of get the same experience impossible. If Dafny didn't do that, if Dafny treated missing or erred on missing cases rather, would you still have gone immediately for these induction principles? Do you think you could have been able to use just matches more often?
No, because this is actually only one of the problems. Like another problem is there is this underscore case where you don't know what's going on. And also in many situations you actually have, so it's not something you see on the list example, of course, but sometimes you just have, you listed all the cases, but for example, you have a timeout. And then you don't know what's going on.
Right.
And so it's very important to be able to split all those small cases into smaller lemmas, for instance.
All right, thank you.
So I guess for mutual induction, I need to write a module that captures a mutual induction principle. Like if I have two data types and they're recursively.
So we didn't try it with mutual induction. I guess I don't see why it wouldn't work the same way.
Okay.
But one would need to try it. The important thing is yeah, I think it should work. You just need to list all the cases.
And in this example where you've changed to sequences,
Yep.
did you have to write an induction principle for sequences as well, or are you using now Dafny's?
Yeah, so yeah, that's a good question. We had to, so whenever we made a co-modification, we have to update the induction principle. And in this specific case, we had to introduce lemmas which correspond to an inductive principle for sequences. So indeed, we have some sort of a mutual induction. And the good thing is, as you can see, the proofs went through automatically, because once again, putting aside the problem of setting up the inductive structure of the proof, Dafny's automation was able to take care of everything.
And one last thing, could you imagine Dafny generating these for you automatically as Coq does for its own induction principles?
So I totally imagine that in the case of data types. However, for the interrupt statement function, we're actually encoding an inductive relation, and this is a lot harder to automate.
Yeah, I think we have to move on.
Okay.